Hello everyone, in this video we're going to look at the largest rectangle in a histogram problem. The problem is that we're given an array of heights which represents a histogram, and our job is to find the largest rectangle which can fit in this histogram. So if we're given this array, the corresponding histogram would look like this, and the largest rectangle for this histogram is 3 wide and 2 high for an area of 6. And if we're given an array like this, the histogram would look like this, and the largest area would be 7, with this rectangle of height 1 hiding on the bottom here. Let's look at how we might solve this problem with a brute force solution. The idea behind the brute force solution is to just compute all possible rectangles that could exist. So we could start off with an I pointer on the left end of the histogram, which symbolizes the left end of the rectangle we are computing. We then can add a J pointer, which symbolizes the right end of the rectangle. Initially, J starts at I, so there's a rectangle of width 1. We then can continually move J to the right, computing rectangles along the way. But one thing we have to be careful of is that the height of a rectangle is restricted to the smallest bar. For example, here, we can't compute a rectangle of height 2, it has to be 1 because the height is restricted by the element in the second position. In order to keep track of this, we need to keep a running minimum of the heights encountered so that we can use it when we're computing the area. The way we're going to compute the area is just width times height. For width, it's the J index minus the I index plus 1. And for height, it's the minimum height, which we were talking about just a second ago. Multiply these two and we'll get the current computed area. We then compare this current area to the running max to see if it should take the place of the maximum area encountered so far. The running time of this solution is quadratic because we have the I for loop, which runs for n iterations, and we have the nested J for loop, which runs from I to n. Now that we have discussed the brute force solution, let's see how we can improve its running time. Let's go back to our brute force solution and see where it's wasting time. The primary reason our brute force solution is not efficient is that it doesn't remember information that it learns while iterating through the histogram. More specifically, it doesn't remember where certain rectangles of certain heights start and end. For example, let's say our algorithm just finished the last step of the first iteration of the I for loop. What is something it could have learned? Well, it could have learned that a rectangle with height 1 can have a left boundary at the very beginning of the histogram. So then we can see how when it moves I over by 1 and begins to compute these rectangles of height 1 with left boundary at the second element, the algorithm is not doing anything useful because for any of the rectangles it computes here with height 1, a larger one already exists where the left boundary starts at the first position rather than the second position. So how can we fix this in our improved solution? Well, our improved solution is going to make use of a stack to remember and keep track of certain starting points and heights of certain rectangles. On the right is our pseudocode. We're going to have two stacks. The first stack, P stack, is going to keep track of the starting position of any rectangle we want to track. The second stack, H stack, is going to be synced with the P stack to record the height of the corresponding rectangles that we're tracking. It might be a bit confusing right now, so let's trace through this example and I'll develop the pseudocode as we go along. First, we're going to have the same I pointer, which is going to iterate through the heights list. Now we want to begin tracking this green rectangle of height 2 here. So let's push the appropriate things to the stack. We're going to push a 0 to the P stack because this green rectangle starts at position 0. And we're going to push a 2 to the H stack because the height of the rectangle is 2. Let's move on to the next iteration where I is on the second element. Now according to our current code, we would be pushing a new rectangle onto the stack. Now this isn't completely wrong because well there are two rectangles of height 2 we could be tracking here. But it's not completely right either because as you can probably tell, tracking the rectangle is going to be a waste of time because for any rectangle we make with the red, a bigger one can be made with the green. So let's fix this by adding the following condition. In order to add more elements to our stack and track more rectangles, we need the height of our current element to be larger than the height of the rectangle we're currently tracking on our stack. This condition makes sense because it's only necessary to begin tracking a new rectangle if its height is larger because using this larger height, its area could potentially end up being larger than the current rectangle we're tracking. For example, let's pretend for a moment that this second element was actually 3 blocks high. Then we would want to push this onto the stack and start tracking this new red rectangle, because it's now possible that this red rectangle could end up larger in area than the green rectangle. But this is what our histogram actually looks like, so let's stick to this. So at this point, with our modification, our stack only has one element. Also, let's quickly add in this edge case where our stack is empty. If our stack is empty, it means we aren't tracking a rectangle at all, and we're going to want to push elements onto our stack. So let's move on to the next iteration, when I is on the third element. Well, at this point, our algorithm needs to realize that the rectangle we are currently tracking of height 2, starting at position 0, is finished, because we are restricted by this element which has a height of 1. To handle this, let's introduce an if condition, where if the top of the current stack is higher than the element, then we're going to want to compute the area. We can compute the area by multiplying the width times the height. The width can be computed as the current right bound, which is I, minus the left bound of the rectangle, and this is the top of the position stack. The height is just the top of the height stack. And now we can compute the area of this rectangle and compare it to our max area to see if it's larger. Max area started out as 0, and 4 is certainly larger than 0, so it can now take the place of our max area. We can condense our area code to this. So now when we exit this first if statement, our stack is empty and our max area is 4. Since our stack is empty, symbolizing the fact that we aren't tracking any rectangle at all, we enter the if statement and begin to track a new rectangle. Our second if statement pushes the height of 1 at position 2 onto our stack, symbolizing that we're tracking this green rectangle here. Now this should be raising some alarm bells, because a rectangle of height 1 does not start at position 2, it starts at position 0. So there seems to be a mistake in our code. We have to realize that if we enter the first if statement, it means that the height of our current element is lower than the height of the rectangle we were tracking earlier. Therefore, we should be using the position from the stack as our new starting point for the lower rectangle, because the taller rectangle, which we started earlier, can now be the new starting point for our shorter rectangle. So how do we fix this? Well, we can keep track of the last position from the stack by using a variable to save it. We can then take the minimum of the last width and I when pushing it onto our stack. Using this minimum technique allows us to elegantly handle the general case of appending to the stack which we saw earlier, and this case now where we're updating the stack after computing an area. Initializing and using a variable in this way will probably cause an error in most programming languages, so we need to initialize the last width variable outside the if statement and set it to some arbitrarily large value. So now, when our second if statement is finished, our p stack and h stack should be correctly tracking a rectangle of height 1, which starts at the very left of the histogram. Now we can correctly move on to the next iteration, and this is when I is on the fourth element. Since this element is 3 blocks high, it's taller than the current top of our stack. So we don't need to compute the area, and we just enter the second if statement, which causes us to push a 3 onto the p stack and a 3 onto the h stack. This means the stack is now tracking 2 rectangles, one with height of 3 starting at the 4th position, and one with height of 1 starting at the 0th position. Now let's move on to the next iteration, where I is on the 5th element. Again, this element is greater than the top of our stack, so we just enter the second if statement. This means we push a 4 onto the p stack and a 4 onto the h stack. So at this point, our stack is tracking 3 rectangles. The one we just added with a height of 4, and the ones from earlier with heights of 3 and 1. Moving on to the next iteration, the ith element is now less than the top of our stack, so we enter the first if statement. The first if statement finishes off the rectangle on the top of our stack, which is the blue one, and gives us the computed area of 4, which is just as large as our current max area, so that stays the same. At this point, our stack looks like this, and our code tells us to move on to the next iteration. But something is wrong with this. Namely, it seems like our algorithm is now tracking the red rectangle of height 3, which starts at the 4th element. This isn't right because it should have been finished on the last iteration, when we encounter the element of height 1. This exposes a mistake in our algorithm, namely the fact that in the earlier iteration, we should have not just finished the blue rectangle, but the red one as well. We need to realize that as long as the current top of our stack is greater than the current element, it means we still have rectangles to finish. To fix this mistake, we can change our if statement to a while loop, so we repeatedly check and remove rectangles as necessary. We also should add this edge check in our while loop, which makes sure our stack is not empty before we peak. Okay, so now our while loop will cause us to finish the red rectangle, computing an area of 6, which is greater than the current max area, so it replaces it. So when the while loop terminates, our stack is only tracking one rectangle, and it looks okay for us to move on to the next iteration now. For our final iteration, the height of the last element is larger than the top of our stack, so we enter the second if statement, causing us to begin tracking a rectangle of height 2 starting at position 6. Since this is the final iteration, we exit the for loop. And the most natural thing for us to do is return the max area. But there's one problem with this. We still have rectangles on our stack that we're tracking, and we need to finish those manually before we can return. To do this, we can inject a while loop, which will finish any rectangles that are still being tracked on our stack. It calculates the area the same way as in the for loop, we just have the right boundary set to the right end of the histogram. In our case, this while loop runs twice. First for the red rectangle, calculating an area of 2. This isn't large enough to replace our max area, so we leave it alone. But for our second iteration, we complete the green rectangle, and this rectangle's area is 7, which is large enough to replace our current max area of 6. So finally, when our function ends, we return a 7, which seems correct to me. And our stack is empty, which means we aren't tracking any more rectangles. One cool thing we can do to avoid the while loop at the end is to add an element of height 0 to the end of our heights array. This will trick our algorithm into finishing any live rectangles, because the for loop will iterate one extra time, where on that last iteration, the height will be 0. So if we do have any rectangles being tracked, we'll be guaranteed to enter that while loop in the for loop, which will empty our stack. Here's the actual Python code. In Python, we can just use a regular list as a stack by appending to push using pop to pop and a -1 index to peak. You can find all this code for the brute force solution and this solution on the Knapsack website, which I've linked in the description of this video. Finally, let's move on to analyzing the time and space complexity. For time, we have the outer for loop, which is n steps, and although we have a nested inner while loop, this while loop can only be run if there are elements on the stack, and the stack will only be pushed to at most n times, so therefore this while loop can run at most n times over all the iterations of the for loop. So our time complexity is O of n plus n, which is just n. Our space complexity is n as well, because our stacks can grow to the size of n in the worst case of a strictly ascending histogram. I think this solution is a little bit tricky, so it might take some time to understand, but hopefully you leave this video with at least a better understanding of the problem and how we can use a data structure like a stack to approach certain problems. But yeah, that's it for this video. If you have any questions, please feel free to ask in the comments and I'll do my best to get back and answer them. If you found the video useful, please consider leaving a like and subscribing to the channel because all the support really helps. But anyway, thank you very much for watching and good luck on all your interviews.